Water assessment is a systematic evaluation of water physical, chemical, and biological characteristics, determining whether it's fit for domestic, agricultural, industrial, and environment use. As Rahman and Ahmed point out, it's essential for spotting pollution sources and supporting sustainable water management. But it's important goes beyond just safety. Clean water is fundamental to human health, drive economic activities, and keep aquatic ecosystem thriving since it's sustaining biodiversity and preserving ecological balance for the long run. However, studies by Lin and Han show that urbanization, industrialization, and population growth are speeding up water quality decline worldwide. Untreated wastewater, industrial effluent, and farm runoff are dumping pollutants such as nutrient, heavy metals, and toxic chemicals into water bodies. Hence, putting an aquatic ecosystem, human health, and also water security is at risk. To address these challenges, the GIS, Water Quality Index WQI, and remote sensing has become increasingly important. These technologies provide approaches for environmental monitoring that enable informed decision-making and support sustainable water resources management. This documentary will present their application through 3 selected case studies.
Did you know that water is one of nature's most valuable natural resources, supplying drinking water, supporting agriculture, industry, and diverse ecosystems? However, rapid urbanization and economic development have placed increasing pressure on our rivers. Studies show that water quality in many Malaysian rivers has deteriorated, with some rivers requiring substantial treatment before the water is safe for consumption. This highlights water pollution as one of the country's most critical environmental challenges. The degradation of river water quality is mainly driven by human activities. Scientific studies have identified industrial wastewater, untreated domestic sewage, agricultural runoff containing fertilizer and pesticide, and improper solid waste disposal as the major pollution sources. In rivers such as Langar and Merbok, researchers found that pollution originates from both point sources like factory discharge and non-point sources including urban runoff and agricultural activities. The consequences of water pollution extend far beyond contaminated rivers. Research has shown that declining water quality threatens aquatic ecosystem, reduces biodiversity, and increases the cost of water treatment. Polluted water also poses health risks to nearby communities and may disrupt the supply of clean drinking water. These environmental and social impacts highlight the urgent need for effective monitoring and sustainable river management.
So now we will be discussing why we need a better monitoring system. First limitation is limitation of spatial and temporal coverage, where the current monitoring system can only be conducted on specific locations, not across a rivers or basin. Also, it can only be conducted weekly or monthly. Second limitation is it has a difficulty in assessing remote areas, where the areas that dangerous and hard to get will be difficult for us to monitoring the areas. So the third one will be the human error. There will be many errors that existed during the process of current monitoring system. And finally, the limitation of lack of real-time monitoring, where the current monitoring system can provide a delayed information, so a fast response action cannot be taken to overcome the problem. So, an improvement need to be done to overcome these limitations. So that's why we need a GIS, WQI, and remote sensing, because this system have early detection of environmental problems, where it can detect the pollution before it becomes severe, and also can monitor the change in water quality, land use, and ecosystem. Also, this system have support decision making. It can help governments and agencies develop effective environmental policies. Other than that, this monitoring system can save time and also the cost. And finally, the important one is GIS, WQI, and remote sensing can track environmental change over the time. So it can measure the effectiveness of pollution control or restoration of our programs. So for the study gap, we identified that the use of GIS, remote sensing, WQI, and spatial analysis to assess water can only be used alone and in specific areas. So a better picture of our water quality cannot be provided. So a combination of technology and methods need to be done in order to improve the accuracy and reliability of the data. For research problems, these journalists use the combination idea, where they use GIS, remote sensing, WQI, and spatial analysis to provide a better water quality assessment. So a accurate data of water quality over the large area can be prevented and also can help in improving the ability in identifying the pollution patterns and also supporting the effectiveness of environmental management.
Our first case study focused on the Asar River, an important tributary of the Yamuna River located in Dehradun, Uttarakhand, India. The river support the surrounding Asan wetland, provide water for domestic and agricultural use, and has ecological as well as religious significance. However, rapid urbanization and increasing human activities have placed significant pressure on its water quality, making it an ideal location for evaluating advanced water quality assessment method. Over the years, the Asan River has experienced serious water quality deterioration due to rapid urbanization, industrial development, domestic wastewater discharge, and agricultural runoff. These human activities have increased pollution levels and threatened both the river ecosystem and the nearby wetland. Therefore, a comprehensive water quality assessment was necessary to identify pollution hotspots and provide scientific evidence for effective river management and conservation. To investigate the extent of pollution, researchers collected water samples from 7 monitoring stations and analyzed 14 physical-chemical water quality parameters between October 2018 to March 2019. The study integrated the Water Quality Index, analytical hierarchy process, and geographic information system to provide a more comprehensive assessment of a river water quality. GIS play a key role by mapping the sampling location, visualize the spatial distribution of water quality, applying inverse distance weighted interpolation, and identifying pollution hotspots along the river. The finding reveals significant spatial variation in water quality, with Station 3 identified as the most polluted location due to intensive anthropogenic activities. The analysis also showed the pH, BOD, and DO were the most influential parameters affecting the overall water quality. Overall, the integration of GIS, WQI, and AHP successfully identified pollution hotspots and provided valuable information to support pollution control, river conservation, and sustainable environmental management.
Next, our second case study, which focused on the Gomti River located in Lucknow, India. The Gomti River is an important freshwater resource that supplies drinking water, support agriculture, industry, and millions of people living within the basin. However, rapid urbanization and population growth have placed increasing pressure on the river, making it one of the most polluted rivers in India. The river receives approximately 865 million liters of wastewater every day from 68 major drains. In addition, wastewater from industry such as sugar factories, textile manufacturing, electroplating, and slaughterhouses is discharged into the river. These pollutants have significantly reduced water quality, threatening aquatic ecosystem and creating serious risks to public health. To evaluate the river's condition, researchers analyzed water quality data collected monthly from 7 sampling stations between 2013 and 2017. 12 physiochemical parameters were measured, including pH, use of oxygen, biochemical oxygen demand, chemical oxygen demand, and total of dissolved solid. The researchers then calculated the water quality index and synthetic pollution index to determine the overall pollution level.
To better understand the spatial distribution of pollution, the researchers integrated the water quality data into a geographic information system, or GIS. Using the inverse distance weighted interpolation method in ArcGIS, they can produce pollution maps that showing water quality across the river. Next, we go about the deep learning. Although this study did not apply the deep learning, it can be stated is successfully demonstrated how GIS spatial analysis can transform complex environmental data into clear visual maps, allowing pollution patterns to be identified more effectively. So the result revealed that water quality gradually deteriorated from upstream to the downstream sections of the Gomti River. Many locations were classified as severely polluted and unsuitable for human consumption. The study also identified biochemical oxygen demand and chemical oxygen demand, which is BODE and COD, as the main factors that influencing the quality in the Gomti River. Based on these findings, the researchers conclude that continuous GIS monitoring and effective wastewater management are essential to restore and protect the river.
Our third case study focused on the Huizhuan karst wetland in Guilin, southwest China. It is the largest karst wetland in China and an important freshwater source for the Lijian River. Because this fragile ecosystem is easily affected by environmental changes, it was chosen to demonstrate how advanced technologies can improve water quality monitoring and environmental management. In recent years, the wetland has experienced declining water quality due to agriculture, tourism, non-point source pollution, and increased nutrient and sediment inputs. This activity have caused eutrophication, degraded the ecosystem, and threatened biodiversity that highlight the need for continuous water quality monitoring. To evaluate water quality, researchers collected field measurements from many locations across the wetland. They analyzed 4 key parameters: chlorophyll A, dissolved oxygen, turbidity, and phycocyanin. By combining field data with UAV multispectral, Sentinel-2, and hyperspectral imagery, they used GIS, remote sensing, deep learning, and machine learning to develop accurate water quality retrieval models. The observation was continued by using remote sensing to monitor water quality across the entire wetland with the combination of satellite and UAV images to collect large-scale data. At the same time, GIS was applied to perform spatial analysis to analyze and map a detailed quality pollution hotspot more efficiently than traditional field sampling. To improve monitoring accuracy, the researcher also applied deep learning and machine learning models that includes the transformer, random forest, XGBoost, and Gaussian boosting to accurately predict multiple water quality parameters. The transformer model achieved the best overall performance. Finally, the results showed that the most polluted areas were located downstream, near agricultural land and fish pond. Around one-third of the wetland experienced serious water pollution due to high chlorophyll A and turbidity concentrations, demonstrating that integrating GIS, remote sensing, and AI provides a fast and reliable approach for large-scale water quality monitoring.
Although all three case studies focus on water quality assessment, they differ in their research objective, monitoring scale, and assessment approach. The Assam River study mainly focused on identifying pollution hotspots along the river, providing detailed spatial information to support local pollution control and river management. In comparison, the Gomchi River study placed greater emphasis on analyzing pollution trends over a 5-year period. By evaluating both spatial and temporal variation, the researchers were able to observe how water quality changed across different monitoring stations and over time, providing a broader understanding of river pollution dynamic. Meanwhile, the Gillen Karst Wetland study adopted a different perspective by focusing on large-scale wetland monitoring. Instead of relying mainly on conventional field sampling, the study estimated multiple water quality parameters using remote sensing data collected from UAV and satellite together with artificial intelligence model.
In conclusion, all three case studies demonstrate that integrating GIS, water quality index, and remote sensing improve water quality assessment compared with conventional method. The Assam River and Gomchi River study successfully identified pollution hotspot and assessed river water quality, while the Gillen Karst Wetland study further enhanced monitoring by using remote sensing and artificial intelligence for large-scale assessment. Overall, this integrated approach provides more accurate analysis, wider monitoring coverage, and better support for environmental decision making, making it an efficient and sustainable solution for long-term water resource management. Lastly, for future recommendation, moving forward, the use of artificial intelligence, GIS, remote sensing, and UAV technologies should be further improved to enable faster and real-time water quality monitoring. Strengthening monitoring programs and improving pollution control strategies can help achieve better environmental management. In the long term, these technologies can support sustainable water resource management and help protect freshwater ecosystem for future generations.